Welcome to a presentation entitled Regularized Iterative Generalized Least Squares with Optical Selection of the Hyperparameter for Identifying Nonlinear Phenomenological Models. Reduced order models for capacity fade or state of health prediction for applications in controls of battery management systems are often comprised of a power-like term multiplied by gains and an Arrhenius-like exponential term, which acts as a form of rate constant. For example, the model by Martinez-Lozano et al. In 2018 has the form shown. There are four parameters in this model that need to be estimated from the data: a gain, omega, the power law index theta, and in this exponential Arrhenius-like term, there are two parameters, beta 1 and beta 2, again, which need to be estimated from the data. The issue with such models, although they're physically motivated, is that their multiplicative form makes them difficult to identify. The model is identifiable if it is theoretically possible to learn the true values of the model's underlying parameters after obtaining an infinite number of observations from it. And in the next 2 points, I provide some mathematical details. The key point is the second one, which is identifiability of the model in the sense of inversibility of the mathematical mapping from the parameter space to the statistical model is equivalent to being able to discern the true parameter vector if the model can be observed indefinitely. So let P be a general nonlinear regression model, y equals fx theta plus e, where e is a random error term, and will allow the form of the Gaussian errors to be quite flexible in terms of their covariance function, and we allow for heteroscedastic and serially correlated terms. Mathematically, identifiability of the model comes down to whether the information matrix F is invertible. And F is the Jacobian matrix transpose times the Jacobian matrix, and the Jacobian matrix is obviously the derivative of the fit function with respect to the individual parameters. In situations where there are near linear dependencies among the columns of the Jacobian matrix, the conditioning of that matrix can become very poor. This can result subsequently in very imprecise parameter estimates. Under these circumstances, parameter estimates themselves can be very sensitive to the peculiarities of the training data, implying that a small perturbation in the data leads to a large change in the parameter estimates or even their sign. This is very undesirable, clearly. The inherent sensitivity of the parameter estimates to the data suggests that this problem is ill-posed. An ill-posed problem can be converted to a well-posed one using a regularization method. The concept is to confine the problem to a restricted set of parameters using a regularization functional. Typically, this is achieved by introducing a constraint of the form shown to the usual log likelihood, such that you end up with a hybrid cost function, which is shown there. The form of this is reminiscent to similar approaches used in Lagrangian multipliers in other disciplines. The regularization parameter, lambda, or the hyperparameter as it's often termed, implicitly defines a structure on the possible models by constraining the model parameter values to a subset of the possible parameter space. Low values of lambda correspond to high values of C, i.e. a weak constraint. High values of lambda correspond to a low value of C, i.e. a strong constraint. Hence, we can see that the regularized cost minimization problem represents a trade-off between model fidelity, which is expressed in terms of minimizing the log likelihood, negative log likelihood, and constraining the model to be a member of a small complex subset of the parameter space R theta. Further, the balance between fitting the data and satisfying the constraint is controlled entirely by the regularization parameter. A very common choice for the regularization functional is the ridge constraint, which is just essentially the sum of the squares of the individual parameters to be estimated. Parameter selection is accomplished by minimizing the regularized cost function iteratively using a gradient-based optimizer. Here we're concerned with the optimal selection of the hyperparameter each iteration of the nonlinear parameter search. And this way, we can control the trade-off between fidelity and the constraint automatically as the iterative parameter search proceeds. And this is accomplished by developing a fixed point iteration scheme. These are founded on novel re-estimation formulae derived from the performance criteria BIC and AICC, which are given, where theta is the parameter vector to be estimated, L theta is the usual Gaussian negative log likelihood, gamma is the effective number of parameters, and then the number of data points. Both these measures are smaller the better measures. Using the full likelihood permits comparisons among models in natural and transform units, as well as allowing for the presence of heteroscedastic or serially correlated data. By differentiating the defining relationships for BIC and AICC with respect to lambda, setting the result to 0 and subsequently solving for the hyperparameter, we can derive the following relationships. These are both of the form lambda equals a function of lambda, h lambda. As lambda appears on both sides of these equations, we must resort to fixed point iteration to estimate the optimal hyperparameter. A fixed point is defined if the function h lambda is defined on the interval ab, and in that interval h lambda equals lambda for some value of lambda, which itself is in the interval ab, then the function h lambda is said to have the fixed point lambda in ab. The most important aspect on this slide is the following theorem, which guarantees the convergence of the iteration scheme, provided that certain conditions on the absolute value of the first derivative and the value of lambda are met. And these are the key conditions, that the absolute value of the first derivative of h lambda is less than k, which must be less than 1 for all lambda is a member of AB. So then if lambda 0, the initial value of lambda in the iteration scheme, is within that interval, then the sequence defined will converge to the unique fixed point in AB. And then if the theorem is satisfied, we can actually use this formula to provide an error bound on the true estimate. On this slide, we describe our optimal hyperparameter selection algorithm. It's a trials algorithm. We start by generating 6 logarithmically spaced values in the interval, for lambda in the interval 10 to the minus 5 to 1, and calculate the corresponding absolute value of the first derivative of h lambda evaluated at the trials value. The trials value, which corresponds to the initial value of lambda 0, is selected based on the following conditions. We select the one that has the minimum value of the absolute value of the first derivative of h lambda, which is less than 1. And obviously h lambda itself must be in the trials interval. Within each increment, we then recalculate lambda r plus 1 using either the BIC or AICC formula as desired. And we continue until convergence. To demonstrate the efficacy of the approach, we've generated some synthetic data according to the model shown, and the true values, again, are quoted there on the slide. To make things as terrible as possible, we've kept T and SOC, the state of charge, constant throughout. So this Arrhenius-like term is in fact itself a constant, which is terrible from the mathematical conditioning viewpoint. To make things also a little more difficult, we've allowed for heteroscedastic noise with the parameters shown. So on the right hand side here we have the usual regression diagnostic plots, and this plot quite clearly shows we've done a reasonable job of dealing with the heteroscedasticity in the data, and that the fit looks quite good. So in this table we provide the estimates at convergence for the individual parameter estimates, and also 95% confidence intervals. Now, in all cases, the confidence intervals are reassuringly narrow, which is very good, so we're quite precise, but neither algorithm provides confidence intervals that span the true value of the parameter in all cases. And this is due to the inherent bias which is introduced into the method by the presence of the regularizer. And again, looking at this bottom table, just to again give a sense of what's going on. This is the optimal value of the regularization parameter. This is the condition number of the Jacobian matrix at the initial value of lambda, and this is the final value of the condition matrix at convergence, and this is the effective number of parameters, which, as you can see, is nearly 2, and that's not surprising since the beta 1 and beta 2 terms are amazingly confounded with the omega term, so this can really be collapsed into a single parameter, which leaves just this one to be estimated. In this slide, we examine the convergence rate of the hyperparameter selection algorithm, and what this really shows is the efficacy of the trials algorithm, because if you choose the right value of lambda, then your convergence is much more rapid. And obviously the initial value of lambda determines the initial value of k. And the smaller the value of k, the faster you converge to the true value. So the optimal hyperparameter estimation method presented is efficient and converges rapidly, giving a suitable starting position. The smaller the initial value of the absolute value of the first derivative of h lambda, the more rapid the conversion. Selection of lambda 0 using a trials algorithm allows a fast and reliable method of determining if convergence is both possible and rapid. The fixed point iteration formulae presented are suitable for general covariance structures. A simulation study demonstrated 95 confidence intervals for the parameters for the Martinez-Lacerna model, which were reassuringly narrow, but neither the BIC or the OIC method included the true values in all cases. This demonstrates the inherent bias in the regularized estimator.